Welcome back to a rainy day in Thailand. We are currently getting pummeled with monsoon rains, and I'm already getting tired of it. But picking up from the last video, if you remember, I decided that what I really need is a way outside of the Arduino board itself to read differential analog voltage values. So that means I'm reading a value which is independent of the ground in the system. I can pick any 2 points and measure the voltage between them. So I started doing some Googling, and I came across this blog post from Henry's Bench. And what he's talking about is a module from Adafruit called ADS1115. And what this provides is a tiny little circuit board that has 4 analog inputs, but you can also manage it so that you have a differential input between 0 and 1, and then 2 and 3. And this is exactly what I'm looking for. So thank you, Henry, for this great explanation and introduction to the board. So I went ahead and I found a place in Bangkok that actually had these in stock, and they were half price. Now I need to read 6 voltages, so given that I have 2 differential inputs on each board, I need 3 boards, but they're half price, so I ordered 5. So let's take a look at the actual little chip on the board that does all the heavy lifting. So here's a diagram from the Texas Instruments page for this chip. You can see it's the ADS1115. We have the analog inputs over here, which goes through a multiplexer. And what that does is it allows the analog reading circuit to be attached to one or more of the pins as needed. So it helps add more inputs by simplifying the circuitry inside. After the multiplexer, the next step is a programmable gain amplifier. And I'm not going to use this. I'm just going to leave it at its default. But what it allows you to do is scale the voltage reading up or down depending on your needs. Now, I need to read anything up to about 4.3 volts. So the default of 6.144 volts is perfect for me. If I needed to measure a maximum of 1 volt, I would use the gain amplifier to scale the voltage such that the readings were more accurate in the 0 to 1 volt range. So that's what that does for us. Now the analog inputs then come through to this 16-bit, and it's called a delta sigma analog to digital converter circuit. This is quite common in the world of analog to digital conversion in silicon chips. It's a very high quality, essentially algorithm that it gives you good samples. So I'm going to be happy with that. Now this digitized number that's going to be for this particular chip, it says it's a 16-bit reference, but one of the bits is encoded for either the negative or the positive value of the voltage. So we really only have 15 bits to describe the actual number, which is going to give us 32,767 distinct sample levels, which corresponds to 0.1875 millivolts for each tick of the output of this converter. That's slightly less than 2/10 of a thousandth of a volt. And damn, that is very, very high resolution, far more than I need. But hey, it's here, it's cheap, it does the job, so I'm just going to stick with it. Now the digital value comes out and it's put out onto what's called the I2c bus, which goes through this clock and data pins. And then I can read that in with my Arduino. Okay, now let's jump over and see how the board is implementing this chip. Okay, and here we have the board. We have the 16-bit version and the 12-bit version. Here's this Texas Instruments chip, and these are tiny surface mount components that basically give it a nice clean power supply and signal conditioning for the various outputs for the board. So That's all you need. You have a tiny little pin header that comes with the board. I soldered that into place, and then we can get going. So we reviewed this before. Now, the cool thing about the I2c interface is I need 3 of these boards in my system, but how do I tell the Arduino which one to read from when I want to do an analog voltage reading into my code? Well, the board allows you to select one of 4 addresses, which are 4.8 hex, 4.9, 4A, and 4B. And I'll show you how that works. One thing I've always liked about Adafruit is they have incredibly well documented features that come with every one of their products, and this little board is no exception. It's got basically step-by-step instructions on how to wire it up, and then these little graphic guys show you how to wire each of the input pins, and this section here is explaining the I2c addressing. So let's take a look at that. Using only one pin on the board, it allows you to select the hex address of the board that you're going to read from. So address number 48, you connect the address pin simply to ground. That tells the board your number hex 48, and you should respond on the I2c bus for commands for that board. For hex 49, you connect the address pin to +5 volts. That's easy. Now, it gets a little weirder here. For address 4A, you connect the address pin to the data line of the I2c bus, which means to figure that out, the TI chip needs to watch the I2c data line and compare it to the address pin to see whether or not it's address 4A. And similarly, for hex 4B, you connect the address pin to the I2c clock pin. And so after connecting up 3 boards, I'm going to have something like this little cascade diagram here. And for the Uno, which they've very helpfully shown me a graphical picture of, the I2c bus clock and data pins are right here on the board, so I simply connect that here, and then I wire up the other boards in exactly the same way. So connecting up the analog signal values is just as easy, and it's got great explanation for how you do this too, both for the single-ended connection, which is an input pin to ground, or in my case, the differential connections. And this diagram here shows that A0, it's very difficult to see, but analog input A0 and A1 are reading the output value from a battery charger board, I believe this is. Yeah, for lithium polymer boards. This is reading the battery voltage back into the Arduino. Couldn't be easier. Now, where a lot of these small, cheap projects fall apart is their software support, but Adafruit is quite good. We had an initial problem way back with one of the Adafruit Bluetooth modules, but this board has a library associated with it, and you simply download it. They provide the source code. You download this library into your Arduino IDE, and basically it takes all the complexity of talking between any of the supported Arduino boards and this board, and it couldn't be easier. I'm so impressed. And once you have the library installed into the Arduino IDE, you start writing your code. You first include wire.h because that's the standard included header file that helps you talk with I2c devices. Then you include the Adafruit ADS1015 header file, which comes from the library we just installed. Now, to talk with the board, the first thing you need to do is create an object representing that board. So you declare an Adafruit ADS1015 or an Adafruit ADS1115, and you give your object a name. And this structure, or this format, will give you a device that sits at the default hex 0x48 address. If you want to select one of the other addresses available, then you need to put the hex address in the constructor. Then in your setup method, you simply take your variable name and you say .begin. And you cannot believe how much code is behind this little begin statement. It still boggles my mind how easy some of this stuff is. And so now we have, in my case, 3 of these boards installed, wired, and sitting, humming, waiting in the code. And the library gives me my 2 differential input readings. The first function reads the voltage between pins 0 and 1. The second function returns the voltage between pin 2 and 3. And it just couldn't be any easier. So if we look at their sample code, they declare the object for the board. They perform the begin function, which wakes up the board on the I2c bus. And then they read a voltage between pins 0 and 1. That's all we need. So let's take a look at my hardware setup. Now, along with the order that I got of 5 of these little Adafruit boards, I also bought just a little bit of breadboarding jumper wire because I ran out. I got a lot of loose ones. I got ones that are in strips, which are really super easy to use, and they have different ends, female to female, male to male, and male to female for use as needed. And then these little packs of pre-bent wire that you can use in your breadboard, and I'll show you the power of how these guys work. Okay, now here's the updated wiring system. You can see I removed all the analog inputs from the Uno. I've kept the relay controls, and I've also added the I2c bus data and clock wires. Now if we come over here, you can see the 3 analog input boards, and this is where the power of these pre-bent jumper wires comes into play, because I needed to run +5 and ground to each board, and I needed to also run the I2c data and clock signals to each board. And also the breadboard doesn't have a complete strip all the way down for these 2 pins, so for every section I had to put a little jumper in. But this is gets me the needed signals without cluttering everything up too much. Then you can see the wires, like this group of 3 coming off this board, which is at address 48, goes over to and solders on to certain points on the resistor board. This is purely for convenience, so I don't have to mess with the wiring of the actual battery holder. Each of these wires is the connection across the positive and negative of the battery terminal. And since I'm measuring 2 batteries in series for each of these boards, the middle wire is common. Now, if we have this red and the blue, or the orange is the positive of the first battery and the negative of the first battery. But the blue is also the positive of the second battery, and the yellow is the negative of the second battery. So that actually works with the circuit because it's reading each of the 2 channels independently, and they can share a common wire, which is super powerful. And then the last thing we have is the clock and the data pins for the I2c bus. Everything else is pretty much the same. The same relays, the same resistor board, and the same battery holders. So let's take a look at the code and see what changes I made. Okay, now the board is wired up and I'm running my code. I have the board initialized with the I2c bus and the Adafruit board headers loaded. I have constructed the 3 objects for our 3 boards. at address 48, 49, and 4A. I have done the initialization on board 0, 1, and 2. And we come down in the code and I do the differential read from pin 0 and 1 of board 0, and I just immediately print this out. This is an int16_t variable, and now you're going to see the problem. We're just reading -1. No matter what battery I plug into that, and I can test with my voltmeter that the proper voltage is going to the input pins on the little board. This is not good, folks. -1 is a generic error code in the world of programming. It means generally some error has happened. Now, I don't know what error that is. Could it be an error? The first thing that's going to happen is it's going to go through the Adafruit board library, through the read code, which is going to be packaged up and sent over the I2c bus to the board as a command. The board's going to read that command, understand that I want to do a differential voltage read. The chip is going to read the voltage across those pins, interpret it, package it up, send it back across the I2c bus, and then pass that converted value back to my code. I'm getting a -1. Something went wrong, and it's not giving me a single hint of where the problem is occurring. There is nothing in the Adafruit web pages about error handling. So we need to go to the next level. Let's check and see what the signal looks like on the I2c bus. Welcome back to a sunny day in Thailand. To you, only a couple of seconds have passed, but for me, it's been about 3 weeks. Several factors have come into play. I started going to the gym, which takes a significant amount of time every day. But I've also become very disenchanted with this project because at every turn something goes wrong. And I'll explain to you the latest one. I figured out why I was getting that -1 command, return code from the analog read. I have this USB-based oscilloscope from RS Pro. So the hardware is here. It delivers all of its data over the USB bus from these input things, just like you would normally see on a regular oscilloscope. And then the software running on the laptop displays the waveforms. And it also, and the primary reason I bought it, is it because it decodes CAN bus, which I will be needing in the future. But it also understands the I2c bus. So when I put the probes on the bus, it was weird, and I can understand why there was no clean data getting back to the Arduino Uno from the analog boards. And I finally figured it out. It was because early on, remember I said I would power the board with USB from the laptop, but I would have a secondary power coming in to drive the relays and all the circuitry on this board. That was my problem. When you're driving the I2c bus from 2 different power supplies, their voltage logic levels don't match up. So as soon as with these 2 wires, as soon as I started driving the analog read boards from the voltage coming off the Uno, boom, I started instantly getting data. But that took me like 2 days of debugging until I finally decided to try something crazy, as normally happens with any engineering project. Now I'm getting voltage readings, so let's actually take a look and see where we are today. Okay, in order to understand our voltage readings, let's take a look at 2 randomly chosen battery cells. So number 39 is 2.959 volts, and number 44 is 3.203 volts. Okay, here we are. We're actually reading voltage, and it's right about 0 You know, as you would expect in an open circuit, they're floating around 0. Let's try cell 39, which is 2.959 volts. Right there, 2.953. So it's actually off by 0.006 of a volt, which is fine with me, but I can go ahead and apply the scaling and the slope of the line thing like I did before. But we're just looking for anything at this point. Okay, I'm switching to number 2, 2.953, switching to number 3, 2.952, switching to number 4, 2.953, switching to number 5, 2.953, switching to number 6, 2.953. Okay, now let's try cell number 44 in slot number 1. 3.196, which is about 0.007 too low. Again, scaling is probably going to take care of this. But now let me plug in cell 39 in slot number 2. So we should see 3.196 and 2.953, or whatever we were getting before. So there goes slot 2. You can see that number 1 has dropped down to 3.118, and number 2 is showing 2.495. They're both wrong. How can this possibly happen? I'm going to unplug cell number 2, and it jumps up to 3.196, which is close to what we had before. Now let me put 39 in number 1, 2.952. I'm going to put 44 in number 2. Number 1 drops down to 2.876, and number 2 is 2.709. This doesn't make any sense. There's supposed to be 2 independent voltage sensing channels, and I'm definitely below the 5 volt supply voltage on each of the input sections. So what's going wrong? Okay, so now we're back in debug mode again for something that shouldn't be my problem. Number 15 is the one we've got. It's got the 4 input pins to drive the 2 A to D sections. Oh, but look! It has a mux into a single 16-bit analog to digital converter. Is this my problem? If they cheaped out on their design and they've got a mux driving a single chip, could this be my problem? I don't know. Let's check something else. Now, the next thing to look at is the Adafruit software that I'm using to talk to the chip. It comes in this library, which is actually hosted on GitHub, which is good of them to make all their stuff open source. Now, if we scroll down, the library doesn't have that many files. And if we look at the actual code file, this is this C++-like code that runs on Arduino boards. It is 5 years old, which is about the time that they made the board. So basically, they made the board, wrote the code, published it, and haven't touched it since. That's always a little scary. This is a compatibility list. Everything's just fine there. But that worries me a little bit. It either means it's rock solid or they just don't care. Now, I did some searching and look what I found. Well, if we look at the open issues list against the GitHub code, you'll see there's quite a few things they've listed here. And digging deeper, there's this guy who has, on his own, decided to basically add a whole bunch of extra functionality to this library and fix a bunch of problems and add more code for things the chip can do that Adafruit chose not to implement in their library. And he has, in the glory of open source, released his library as this, SolidGen 2010 Adafruit ADS 1x15. And his code is only 2 years old and has a bunch of extra functionality. So Short of this being a hardware issue, I'm going to go ahead and load this library in because the Adafruit people said, we're not going to change our code, you go ahead and do what you want. So let's see if that makes any difference. Okay, I've replaced the library with the new one, and we're going to test the voltage. Cell 1 we have 2.952, which looks good. I'm going to plug in number 44, which is 3.203, and nope, same thing as before. The first cell voltage drops down, and this is about half a volt below where it should be on cell number 2. So don't think it's a software problem. I think it's a hardware problem. And it's either Texas Instruments or me, and I'm betting on me. TI is a big company, they're pretty smart, and I'm probably doing something wrong. So let's try one more test. So what I need to do is find a voltage source that when the two are added together, it's less than the 5-volt operating value of the chip. So I've got two AA batteries. One is 1.570 volts and one's 1.604. So I'm going to put them in the battery holder, and with the magic of adding a very large bolt to make up the space, battery number 1, 1.568, that's 2/1000ths of a volt off. Now I'm going to connect the second battery in slot number 2, 1.602, and you'll notice the first cell didn't change, 1.568. So that's it. It's a hardware limitation, even though each of the analog differential inputs should supposedly be able to read up to 5 volts. They can't independently each read a different 5-volt reading. Because when I put my two cells together, that's going to usually take me up to about 6.5 to 7 volts if I'm at 3.5, maybe even up to 8 volts for a 4.2 volt cell. So I have run into a hardware limitation that effectively allows me to use one channel of each of these boards. And that's okay. I'm sure somewhere buried in the 53-page spec sheet, it explains that in analog engineer terms. So, but the obvious solution for me is just to use 6 of the boards and to use one input channel off each board. But, ta-da! The chip itself only has the capability to put 4 devices on the I2c bus. Because of the way it uses this address pin, you can only connect it in one of 4 different ways to be recognized on the I2c bus. So that 4 is not equal to 6 or even close, even when you're doing project budgeting. So what do? I think I need to go to a completely different solution for the analog input, or I run 2 Arduino Unos, each of them driving 3 boards. And that solves my problem without investing a whole bunch of effort into buying new boards, writing new software, and all that. So I think that's what I'm going to do. It's a good time to be a lazy engineer when I'm smashing my head against the wall. So that'll wrap it up for this lengthy video until I get 3 more of the boards and find myself another Arduino Uno on my shelf and get it up and running and put them both in parallel. So wrapping up for now. As you stare out on my beach, I would ask you to subscribe to my channel and click like on this video so YouTube thinks I'm worthy again, and I have so many people on my channel that they'll give me 10 cents a day in ad revenue. So I thank you for that.